Hello everyone, it's July 26th. Okay, we have a problem from yesterday that we hadn't finished yet. So hopefully we have some time left to basically debug this. I still think my method is correct. We'll have to see what went wrong. But it has to be like an easy problem today, which it is. So that definitely helps. All right, let's see. What's today? Count hills and valleys in an array. So we have an array. And index I is part of a hill if the closest non-equal numbers, closest non-equal neighbors of I are smaller than nums I. It is part of a hill if the closest non-equal neighbor, so equal doesn't count, has to be non-equal neighbor, so the peak can be flat. They're smaller than nums I. Similarly, an index I is part of a valley if the closest non-equal neighbors of I are larger than nums I. Adjacent indices are part of the same hill or valley if they're the same. Note that for an index to be part of a hill or valley, it must have a non-equal neighbor on both the left and... Wow!
Well, now what? The categories? Well, maybe they won't see it.
I think this is the biggest spider I've seen.
No, we've seen like a long leg.
Oh no, this is amazing.
Now what?
Well, we hope the spider can climb higher. Wow. No, it's a beautiful spider is beautiful creatures.
It wants to go inside.
That's fine if he wants to. Not sure if it's a he or she, but
Or get angry and say, oh.
no. That's a natural reaction.
What?
Because it have a lot of legs. We don't like things with a lot of legs.
Really?
Really? Because our ancestors got bitten and then they start. I think the spider found home.
Is it a hole?
There's a little crevice. Maybe it can stay hidden there.
Is it gonna die? Or what is it going to eat?
Oh, we have bugs in the house.
You do?
Yeah, we just didn't see them. Yeah, the reason we don't see them because of the spiders. And that's why we love spiders. I love spiders. They reduce the chance of all these little critters coming. Plus, compared to the spiders in Australia, which is like this big, I think these are very benign. And then the one in Australia that big is also very benign. And some Australians actually have them as unofficial pets, and then just they catch cockroaches and then give it to that spider. This is the biggest I've seen here, at least, I think. Yeah, I think it's getting deeper into the crevice. That's good. Alright, you enjoy. Okay, what's the problem of this? We need to return the number of hills and valleys. Number of hills and valleys. So we start and then, but the first one doesn't count, does it? So adjacent, right? We do because so a transition from negative to positive, and then transition from positive to negative. That's the way to go. So what we're gonna do is we'll do. So we have 2, 4, 1, 1, 6, 5, right? So I don't care about this. I start from the second one because the first one doesn't count. So second one is a bigger, right? So it's bigger. So I can say the pre is a 2. Difference is 2. And next one, difference is -1. So the 2 are different. So we got 1. And then this, so like now it's -1. Now this is 0, so I don't count. I keep -1. And this is 5, so we have a difference. So maybe it's easier if we just do 1 or -1. So this is, I can call it, or larger than 0. Is it up? A diff. Diff. Is diff positive? What should I name it? Diff positive. So this will be true. This will be false. This will be true. So we have this. So we have a second one. And then diff is positive will be false. So we have a third one. I think this should be fine. Right? This should be fine. So we can do this. Diff between adjacent numbers. Track their track whether there is a change in in positive, negative, changing sign. One. Boolean value positive is positive. I think at least 3. So this should be nums y minus nums, not I. It should be 1 minus 0, right? That is actually, if they're the same, what do you say? You say true, you say false. I think we probably will be easier just do int pre-diff. Or I can just call it diff. This is actually maybe easier. Okay, so now I can go actually through the second one, right? So what I do is if nums I is equal to nums I minus 1, then we'll continue. Right, I say if nums I is larger than nums I minus 1, if this is larger than the previous, and so the current is larger than previous, and it's the diff, and diff times just say if diff times nums I minus nums I minus 1. If this is smaller than 0, which means the sign is different, then we do rest plus plus. Okay? And we will update. We always update the diff. Right? We always update the diff. It doesn't matter. We just always update diff. And at the end we'll return rest. Alright, give it a roll. Keep on rolling, rolling, rolling. Rolling, rolling, rolling. Keep on rolling, rolling, rolling. Rolling, rolling. Wait, what? Huh. Ah. Anyway. Okay, so this one is done. We're gonna move on to debug yesterday's problem. I'm just curious, like why this one is wrong, right? So if I sort them, we have 222, 721, and 817. So in total is 25, right? So 25. So the total is 25 times 26 divided by 2. What's that? What is 25, 26? 25, 26 divided by 2. 325. That's what we have in total. So now, belonging to this is from 2 to 20, so we have 2 on the front, and we have 4 on the other side, so we have 8, right? So now for this, without overlapping, so it would be 3, right? So, 7 minus would be 5, we have 5 of them. Hold a second. So we have a situation of this 2 to 22, and then a situation of 7 to 21. And then we have an 8 to 17. Okay, that might be the reason why it doesn't work. So these all work from to 21, right? 1 to 21, 2 to 21, everything to 21, they all work. And extend. So what does not work is like 1 to 22, right? 1 to 22, which means in this case we can say start from the left. I just don't get beyond this, right? So what I do is I start from the front, but I don't go beyond. Or I start from 3 and I do go beyond. That's the two scenarios. Okay. Let's try. Okay, let's try. Let's say we remove the first. Okay, remove 0. So now this has full 7 times 25 minus 21 is 4 times 5. So I have 35 of this. Okay, Now for here, I say I'll extend all the way to the left, but I don't go across this. Right, I don't go across this. So I have 8 on the left hand side. Right, 8 on the left hand side. Here I only have 20, so 17, 18, 19, 20. So 21 minus 17. So we got 4. Okay. I now go beyond, but don't go on this side. So that's actually only 1 times, so I have to go beyond, beyond 21, right? So this is, I cannot, but this has to go beyond this, because if I don't go beyond, wait, hold a second. It's fine, it's fine. Because I start from here, I can do anything. So 17, 25 minus 17 is 8. So 8 plus 1 is 9. So times 9. Okay? Do I have another one? So I start from here and then don't go beyond 17. Right? So always stop at 17, but I also don't go to, well, I do go to 8. So 117, 118, 119, right? So we just don't go beyond this part. So I have everything. And then I say, yeah, I think you're double counting. So start from on this side, right? And if it's smaller, then we end it here, right? We end it here, we don't go beyond, we end it here. We don't go beyond this. But we can, right? We can, we don't touch this, right? We don't touch this, okay? So we get everybody that we can fulfilled here, which is 8 times 4. And then we say we have to go beyond 21. We have to go beyond 21 because everything that don't go beyond 21, we have already captured all of them. So now we have to go beyond 21, then this can only start. So this actually is 21, so this is actually 4. No, actually 5. 21. So yeah, 21, 21, 22, 23, 24, 25. So it's actually 5. So I think this is actually 5. This will give you 32 plus 5 of 37. Right? So you add them together is 72 and 325 minus 72. That's 283. No. That's only 243. Okay, that's when we remove this. Okay, now we say let's remove 1. So for this, I got 2 on the right hand side, and 25 minus 22 is 3, so I have 4, so I have 8. I remove this, so basically it's this and this. So again, what we have is we start from here and we don't go beyond this, right? So we start from the front, which is going to be 8 again times, it's 22 minus 17, right? 22 minus 17 is 5. I got 5, so basically 17, 18, 19, 20. Okay, that's actually not 5, that's actually 4. That is actually 4. Wait, hold on. 17, 18, 19, 20, 21. Don't count 21 as 4. This is 17, 18, 19, 20, 21, 22. Don't count. Yeah, it's 5. So we can get 5 of this. Plus, it should be from 22 towards the end. Right? So I have to start from within, but have to go beyond. So this will be 6 on here, 6 on this side. 3, 4, 5, 6, 3, 4, 5, 6, 7, 8, right? Times 25 minus 22 is 3 plus 1 is 4. So this is 40 plus 24. This is 64. Lordy. This together is 72 again. Huh. Okay. Now remove 2. So remove this. Again, we'll have 2 times 4 equals 8. Now for here, right? Here it's 7 times 1 plus 5 times the bigger of the 2. Right, bigger of the 2 is this, which goes as 4. So this is 7 plus 20, so that's 27. 27 plus 8, that's 35. Which is 290. There we go. I'm actually thinking, like, if I have a bunch of this, right, you cannot based on this. Right? You have to base on the largest end. You have to keep track of the largest end. So let's say I go from this to the previous neighbor. Oh, the previous neighbor. Like I have to reach myself, right? So from the start, I have to reach myself. It depends, right? It depends. Like if the previous is bigger than me, then I need to know how much I can go. So I need to know the largest one, that is the smallest one that's bigger than me, right? I need to know the smallest one that's bigger than me, because like I cannot go beyond. Let's say this is like say 25, okay? If this is 25, then this has to be dependent on this 21, right? So I need to know the smallest that's bigger than me. I don't know, how do I know that? Maybe we should sort based on end. But I feel like we'll have the same problem. Right? We think we'll have the same problem. So yeah, essentially it is. Like we can always start from the front. Like if it's this scenario, which is what we thought about yesterday, we cannot start from the front because this is smaller, right? So we have to start with, yeah, because this one goes beyond, right? Because this is the starting point. It's the starting point. If the starting point is bigger than your previous, right? If the starting point is bigger than your previous, then you cannot start from the front. You have to start from like within. Okay, but if the starting point, like if I have something like this, right? Your previous is, but you have something that's really huge. So what you need to know is holy crap, how do I do this? It's very complicated, right? Yeah, and this method would not work because it's not just, the relationship is not just with the adjacent one. The relationship can be with a previous one, right? A previous one. Oh, okay. Let's check the editorial. Right, consider a simplified version of the problem. Calculate the number of valid subarrays that do not contain any conflicting pairs without deleting any of them. For the simplified problem, we first enumerate the left endpoint I of the subarray. Then, under the condition that no conflicting pairs are included, we determine the range of valid values for the right endpoint. For each conflicting pair, we assume AK is smaller than BK. If AK is smaller than I, then no matter how J is chosen, the subarray will not include both AK and BK. That is correct. If AK is larger or equal to I, then we must have J smaller than BK. That is correct. Based on this, we define B. What is that? B1 equal to minimum AK larger equal to I BK. Okay, so this is the minimum of B such that AK is larger or equal to I. So I give it an I. We want to find the smallest B such that the A is larger than I. That is correct because that is the maximum you can reach. Then the valid range for B becomes, for J becomes, that is correct. Right? Yn plus 1. Oh, yes, because we're using smaller. That makes sense. Okay, that makes perfect sense. Therefore, the number of valid subarrays with left endpoint I is minimum of this, which is the right point, minus I. Really? I am not sure actually. Really? Because valid J, right? J can do this, all the way to here, right? So J minus, should be J minus I. Shouldn't this be J minus I plus 1? Right? J minus I plus 1. Oh, but I'm taking this. This is, it's like the largest. Yeah, because J, the largest J can get is this minus, this one minus 1, right? This minus 1 minus I plus 1. So yes, that's correct. That's correct. So now we need to compute this one efficiently. We use arrays B minimum 1 and B minimum 2 to record the smallest and second smallest value of B among all conflicting pairs where A smaller than B. Then B1 can be found using the suffix minimum of B min 1. Wait a second. compute B1. B1 is the minimum B such that AI is larger than I. The minimum B such that this is larger than this. The second smallest value of B among all conflicting pairs. Okay, that one I don't understand. So what we found to find is what is the smallest B when A is larger. So let's say we sort based on A. Okay, and then if A is the same, we're based on B. Alright, and then I have my current index. Then I can binary search to find where it is, but then I don't know. Oh, I do know. Yes, we'll sort the conflict pairs, right? So we sort the pairs, and then we do suffix min at each position, and then binary search would tell me where AI is larger equal to I. So I find that position. Actually, I think it should be a lower bound. I find that position and I know the minimum B, like among them was the minimum B. And then we can use this to find out the number of valid arrays. Right, the number of valid arrays. So these are smaller than me, right? These are smaller than me, so they don't include. These are larger than me, but I cannot go beyond that. So I know the number of valid subarrays, right? The number of valid subarrays starting from I is going to be this. I know how to do this. Now consider the case where we delete exactly one conflicting pair. Okay, so now I'm going to delete one. So actually, by that, O and log n, we can compute the total number of valid starting from every single position, right? Starting from here, how many valid? Starting from here, how many valid? Starting from here, how many valid? Good. Now we need to delete one of them, right? So we have something we need to delete. Now think about it. If the I is to the left, they will not get affected. So what will get affected is the I is the same starting from here, right? Starting from here. Take it back. If the I is larger, it will not get affected. What will get affected is the I towards this side, like all the I plus 1, all the i's here, including this. They will get affected because this one is deleted. But now what we need to know is whether the smallest value, this is the smallest value, right? If this is not the smallest value, then if you remove it, nothing will get impacted because we still have the smallest. They will still be impacted. They will still be affected, right? But what about the second one? Because when you remove this, yes, these will be affected. But then the next one, no, it won't get an impact because for the next one, it has to be indexes here, right? And we're doing But see, this is not the smallest one, so they will still be bound by the smallest one. And all of these will not be affected by this, and they will also not be affected by this. Yeah, so basically in this case I don't want to worry. If this is the smallest one, now when you remove it, now you need to know the second smallest one. That's why the second smallest one become important. You need to know the second smallest one. And then all of this will need to conform to the second smallest one, right? So essentially, initially I have the smallest one, right? The B min. And I don't really think this can go beyond n plus 1, right? Because conflicting pair is smaller than n, so it will never be beyond. So this is actually not necessary. So basically it's just the b value. So basically b min minus I, right, plus b min minus this all the way, so plus all of this. So I need to find their sum, which I can compute, and we'll have total minus this and then plus the new b min 2. Then I think it will work. Let's just see if this one is right. The value of I is determined by b1 if the deleted conflicting pair does not involve b1. The number of valid subarrays starting at I remains unchanged. Which means you delete this, the total valid does not change. Assume b1 is located at this position. If we define this to record the number of additional valid array that can be gained by deleting the conflicting pair, let b to be the second smallest suffix value, yes. After deleting v1, the new this becomes minimum of b2 and b minimum 2 at this position. That's different from what I had thought. I record the number. Why can't we just use the second smallest? This is, I want to say this is correct. This is not what I had in mind. my mind, I have a smallest and I have a second smallest. I mean, yes, that's just for one of them. But for everything, for all the index I, for everything smaller than I, each one of them need to add this one as well. That's why I think you need to multiply. There should be a multiplier there. Okay, I think let's say multiplier is right. I don't understand this part. The second smallest at each point. I have this point and the smallest, the second smallest, second smallest. And then at that point, I know the smallest, and then it happens to be the smallest. So when I remove it, the second smallest becomes the smallest. Why can't I just use beaming to IB1? What the hell is this B2? Exactly, what the hell is this? What the hell is this? I think we should just use this one, because this is the second smallest B, right? At this position. If we delete it, and at this position, we need to know what is the second smallest. And we get the second smallest, and that will be the one that we will use to do this. So we'll do the second smallest minus this, because this is the amount that we can gain for the starting at I, right? But also we have to go all the others. So we can check how this one is done. So this is beaming 1, beaming 2. They did not sort this thing. Huh. They did not sort it. They did not sort it. What? Okay, I have min and max. Oh, it's different from what I had in my mind. I need to use binary search. This one doesn't even use binary search. Hold a second. That is different from what I had in mind. Okay, what's beaming 1 and beaming 2 again? To record the smallest and the second smallest value of B among all conflicting pairs. among all conflicting pairs. B mean 1, A is larger than B, then B mean 2 equals B mean A, and then B mean A equal to B. So like B is smaller, current one is smaller. So I was still trying to figure out what B mean 1, B mean 2 means. I mean, I understand what it's trying to do. The number of active arrays with the left point I is this. Yes, I understand. So what I need to know is, given this a range, I need to find larger than this, right? This is essentially what it is. I need to find this AK, right, larger or equal to this. What is the smallest? So basically, at index, a certain index, what is the smallest B you can find? What is the smallest B you can find? So this is starting from A, looking to the right, what is the smallest B you can find? And now we say if the current B is smaller, I will assign it. And this is the smallest. So I'll assign this, I'll do this. Makes sense. If it's larger than this but smaller than this, I'll do, okay, I understand this. Yes, we don't have to sort. So the order is provided by the indices directly. So, okay, that makes sense. So now I know at each position what is the smallest B that's bigger than this position, right? What's the smallest B that's bigger than this position? Okay, so that's fine. Now we need to remove. I mean, we don't really need to remove. We need to compute the total, right? We need to compute the total, and we need to get what is this? Delete count. Huh? What is this? So what I get is the smallest B, right? This one gets the smallest B that's encountered at this position. Therefore, I need to go right to left to find the smallest B that's encountered so far, right? The smallest B that's encountered so far. This says if IV1 is larger than this, because I is going one by one, right? I is going one by one. I think IB1 is pointing to the second smallest, right? Is that what IB1 is? I have really no idea why they use IB1. Hated that IB1. Huh? So at each position, I know the smallest that's starting from this position. I think this is what it means. The smallest that's starting at this position. The smallest that start at this position. The smallest that start at this position. Okay. And then I go. I didn't even get a total. They do get a total. And I know why they need to use min, because we can avoid that by set everybody to n. So, or to n plus 1. So essentially, what we're gonna do is we're gonna find the smallest. At this position, the smallest. Right? At this position, what is the smallest that you can get? And IB1 needs to point into the value, right? IB1 needs to point to the index that gives you the smallest, right? Give you the smallest. And then now we're just trying to find where the smallest is. And what we're saying is, what the hell is B2? B2 is the second smallest suffix value. I don't know. I feel like this is very convoluted. So yeah, so we basically find the smallest. I'm fine with it, but I need to know the index of where the smallest takes place. That I can do. So we say the index, the smallest. If the current is small, okay. I think I know what's. This is messing me up. I think do smaller is easier to understand. So if this is smaller than that, then B2 will be the smaller of these two, and IB1 equal to I. So this is the index that points to the smallest B, right? B1 is the smallest. The index pointing to the smallest, and if this is larger than this, right? It's larger than this, then it will be min on B2. So we maintain the index pointing to the smallest B and B2, right? Index pointing to B1 and we have B2. That I think I understand. I think I understand. Okay, I think I understand. So now I can do this, right? I can do this. This is just at this position, what is the smallest? And then we use that to get the smallest, and then we add the amount that we can get at this position, and then we need to know how much more we can if this one gets deleted, right? If this one gets deleted, then if this one gets deleted, IB1. After deleting B1, what if we have repeats? Yeah, what if we have repeats? Oh, then the second smallest. I don't know. What if we have repeats? And what do you mean by deleting B1? This is something I don't understand. So you delete B1. I guess repeats is fine because we can find the smallest, right? But you're deleting the B1, which is the smallest, and you do it at every single turn. Huh? After deleting. Yeah, so at this point, I know the smallest, right? I know where the index is for the smallest to occur, okay? So let's suppose the smallest get deleted. Then I need the second smallest. That is correct. That is correct. The second smallest. And the gain is the second smallest minus the smallest. That is also correct. So how do I find the second smallest? So at this position, I know the smallest is somewhere, right? And then I also need to find the second smallest. I say, if the smallest gets deleted, if the smallest gets deleted, then the second smallest becomes the smallest, right? The second smallest becomes the smallest. So we have the second smallest, we have the smallest, and we say if the smallest gets deleted, if the smallest gets deleted, then it's the second smallest. Which means if at this position it happens to be the smallest, okay, so you go to I, and what about B2? B2 will be the minimum, so B2 will be this, right? B2 will be the minimum of whatever I mean. So basically it's saying that B minimum is equal to B min 1 I. They are equal. Then B2 will equal to this. Then that's not the second smallest. It's essentially saying, as we go through, I have a suffix minimum, right? I have a suffix minimum. And at each position, I find the smallest one that's bigger than me. And if the smallest one that's bigger than me is bigger than the minimum, then the number that can be included starting from here is always plus equal to that, right? Nothing gets deleted. It's always going to be bounded by this. Always going to be bounded by this. But I delete, and what are you deleting? That's the thing. What are you deleting? Deleting count. So IB1 is pointing to the index of the minimum. It's if this one gets deleted, right? If this one gets deleted. It could be anything gets deleted, because if it's some other gets deleted and the smallest doesn't get affected, that it's just not, you don't have to worry about it. So we just say at each position, if the smallest gets deleted, right? If at this position, if the smallest one gets deleted, then what's going to happen, right? If the smallest one gets deleted, right? If the smallest one gets deleted, then I need to know at this position, is this position going to be impacted by it? So if the smallest one gets deleted, then I know B2. Alright, I cannot wrap my head around this one. I might understand it, but I don't like it. I don't like it. I think I'm gonna have another shot by using sort. Like, I understand, but I don't understand at the same time. So what I'm gonna do is I will sort it based on start, and then I'll do suffix min and suffix second, smallest and min for every position, right? And then I'll go from everyone. I'll go from everyone, binary search it to know which one we should use, and then I'll compute the total, right? Then we say if one of them gets deleted, right? If one of them gets deleted, then what happens is anything that's larger, if this one gets deleted, so now look into the next one, right? Basically the restriction based on this we need to get reset. So all of them knows that it's smaller or equal to this. They're restricted by this value, right? They're restricted by this value. But now they're no longer restricted by this value because this one is gone, right? This one is gone. It's these are smaller, so they don't worry. Right, so now this one's gone. Now we're looking at the next one. Wait, hold on. Binary search. Starting from, right? Starting from here, it gets affected by this. Oh, it gets affected by this. So if I remove one here, it depends, right? If the one I remove, oh, okay, yeah, this probably didn't work. All right, I think I have to revisit this. I still don't quite understand. I still don't quite understand. Alright, anyway, so, but this is wrong. Okay, this is wrong. I don't think this one will work. But I have to go through this is it's a pretty dense. Alright, that's all. That's all. Well. I'll see you guys tomorrow.